Images work like this. Rays of light come from an object. I have a converging lens, brings them to a focus. Three variables. One is the focal length of the lens. That's the distance of the focal point from the lens. I have S, which is the distance of the object from the lens. And I have S prime, which is the distance of the image from the lens. Those are the three variables, S, S prime, and F. And you've had a chance to read about that. The relationship that connects them is this one right here. 1 over S plus 1 over S prime is equal to 1 over F. That's why we use 1 over F to characterize a lens, because 1 over F is the number that appears in the basic equation. It's the power of the lens that appears there. Another piece of the puzzle is the magnification. Magnification is defined as the image height divided by the object height, and it's equal to S prime over S, negative S prime over S. Now this case of the real image is like our defaults. The object distance is positive, the image distance is positive, the focal length is positive. All those numbers are positive. But the image is upside down, as we saw. And the upside downness of it is why there's a negative sign here. The negative sign just tells you the image is inverted. It tells you it's inverted. If you come out with the magnification that's positive, that tells you that the image is upright. That's ultimately what it means for you. When we look at other cases, F and S prime could be negative, okay? Here's a question. A lens can be used to start a fire by focusing an image of the sun onto a piece of flammable material. All other things being equal, would a lens with a short focal length or a long focal length work better as a fire starter? This is the kind of question that we can address. If you're using a lens to start a fire, you're using the lens to make an image of something on a piece of paper. Here's my piece of paper. Here's my lens. What are you making an image of? The sun. So I have sunlight that comes in. So the sun is back here. Rays of light come from the sun towards the lens. They come to a focus and make a spot on the piece of paper. And the spot is the image of the sun. This is an image of a sun right here. This distance right here is S prime. That's the distance from the lens to the piece of paper. The distance from the sun to the piece of paper is S. That's S. Now, the magnification is equal to H prime over H. I want that to be small. I want the magnification to be small because I want the image to be small. If the image is small, all the light gets packed into a tinier image. And so the intensity is greater, okay? That's what we're shooting for here. I want this to be small. Magnification is equal to H prime over H, but it's also S prime over S. I don't care about the fact that it's a negative sign. That just tells me it's upside down. Don't worry about that. You don't care if it's right side up, upside down. Doesn't matter. But I want to make the magnification a small number in order to make this work. And I can do a couple of things in order to make this be a small number. But the easiest thing to change, if I'm going to change S, that's like changing the distance to the sun. That's hard. But I can change this one, S prime. And if I want the magnification to be small, I want S prime to be small. Okay? So I'm going to choose this and make this be a small number right here. Well, my relationship between F, S, and S prime looks like this. 1 over F is equal to 1 over S plus 1 over S prime. 1 over S is 1 over the distance to the sun. And what is the distance to the sun? A lot. And what is 1 over a lot? 0. So this is 0. So I just get 1 over F is equal to 1 over S prime, or S prime is equal to F. So if I want S prime to be small, what's that tell me about the focal length? I want the focal length to be small. Short focal length lens is going to work better as a fire starter. Okay? Oh, yeah. And if I want to make an image on a piece of paper that starts a fire, what kind of image is that? Real or virtual? Real. It's a real image because the rays of light actually come into a focus at that point, and it's a very, very bright spot. It's a real image on the piece of paper. The only way you can do that is with a converging lens. That's a piece that we'll come back to and talk about. But let's look at the other type of image that we have, which is the virtual image. Rays of light don't come to a focus, but you trace them back and see where it appears to come from. This is a virtual image using a converging lens. The equations are the same, but the sign conventions are different. The difference is this. S is positive. That's the distance of the object from the lens. S prime, that's the distance of the image from the lens. For a real image, it was on the other side of the lens from the object. For a virtual image, it's on the same side. It's opposite from our basic case. And so we signify that by making S prime have a negative sign. Well, if S prime is negative and S is positive, negative S prime over S is positive. That tells me my magnification is positive, and that just tells me that the image is upright. And a virtual image of an object will be upright, as we'll see. Let's do a couple calculations to make this concrete. And we'll start with this one. A 2-centimeter tall object is 40 centimeters in front of a converging lens with a 20-centimeter focal length. Calculate the image position and height. Works like this. First off, I draw an optical axis. and draw the lens, and it's a converging lens. I'm going to put the focal point here. This distance is f, and that's 20 centimeters. So f is equal to 20 centimeters. Then the object is 40 centimeters away from the lens. This distance is s. Rays of light go from the object through the lens, and they will come to a focus. And we can see that. If I trace the rays of light, it works like this. Let's go ahead and trace them and see what happens to them. Ray of light comes in parallel to the optical axis, hits the lens. This is one of the special rays. Comes in parallel to the axis, goes through the focal point. If a ray of light goes through the focal point and hits the lens, it comes out parallel. Or a ray of light that goes through the center of the lens keeps on going straight through without having anything happen to it. These three rays have come together at this point. And so this is where the image will form, right here. The image forms at that point. Because if you looked at that, it's like the rays of light seem like they're coming from here. Look at this. Arrow with rays of light coming from it. Arrow with rays of light coming from it. This is a real image. The rays of light appear to be diverging from this point right here. It's a real image. I could project it on a screen. Okay? This distance is s prime. And the basic relationship we have is this. 1 over f is equal to 1 over s plus 1 over s prime. I'm solving for s prime. 1 over s prime is equal to 1 over f minus 1 over s. The only thing I have in this equation are 3 distances. And as long as I use the distances in the same units, everything will work out just fine. So let's go ahead and leave them in centimeters. If we start in centimeters, we'll finish in centimeters. 1 over the focal length, 1 over 20, minus 1 over the object distance, 1 over 40, 1/20th minus 1/40th. Think back to those fraction days. Oh, yes, 1/40th. So s prime is equal to 40 centimeters. And that looks like about what I drew here. I drew that, and it came out about right. I can calculate the object or the image height as well. The image height divided by the object height is equal to negative s prime over s. So h prime, the object height, is equal to h times negative s prime over s. S prime, 40 centimeters, S, 40 centimeters, S prime over S, 1. And so it's negative 1. The 1 tells me the image height and the object height are the same. The negative sign tells me that it's inverted. That's what the negative sign tells me. So if the object is 2 centimeters tall, how high is the image? 2 centimeters. 2 centimeters tall, and it's 40 centimeters from the lens. Oh, let's mix it up, shall we? Now, how about the object is 20 centimeters in front of a lens with a 40 centimeter focal length? Wow. Switch them up, man. Let's do that. Here's how it works differently this time. Optical axis, draw the lens. Focal length is now here. The object is here. Now the object is in front of the focal point. And here's the big difference that makes. Let's draw our special rays again, shall we? Special ray comes in parallel to the optical axis, goes through the focal point. Special ray goes through the center of the lens, and nothing happens to it. These two rays are never going to converge. They're spreading apart, and they will keep spreading apart. So this will not make a real image. What you imagine doing is looking from this side. If I look from this side, I trace the rays of light backwards. They appear to come from this point right here. And so the image is on the same side of the lens as the object, farther away and bigger. But you saw that when you held that magnifier in front of a piece of paper. The image was on the same side of the lens as the paper was, and it was magnified. It was bigger. It was bigger. And so we know this is what has to happen. But the math is slightly different. This distance is f. This distance is s. And I'm solving for s prime. Okay? My relationship is just the same as before. 1 over f is equal to 1 over s plus 1 over s prime. 1 over s prime is equal to 1 over f minus 1 over s, which is equal to 1 over 40 minus 1 over 20, which is negative 1 over 40. And so we end up with s prime is equal to negative 40 centimeters. The negative sign tells me that the image is on the same side of the lens as the object. And it's a virtual image. Okay? That's what the negative sign tells me. So often the case, negatives are basically signifiers. They tell us something. And that's what this negative sign is telling us. Magnification is equal to h prime over h is equal to negative s prime over s. H prime is equal to h times negative s prime over s. S prime over s, negative 40 divided by 20, negative 2, negative of that, positive 2. Object 2 centimeters tall. How tall is the image? 4 centimeters tall. And it's positive 4. And what the positive tells me is that it's upright. Okay? So the negative signs and the positive signs are cues that tell us where the image is and how it's oriented.